And the last method that we have is parallel decomposition method. So this is useful for transfer functions which can be split by partial fraction method. For example, if you take the transfer function is equal to y of s by c of s, output by input is equal to some numerator function divided by s plus a1 into s plus a2. Now if you split this into a partial fraction, then let us say you are getting k1 by s plus a1 plus k2 by s plus a2. Of course, the numerator will depend on what is the order of n of s, but still this is what we will assume for now. Okay. Now you can consider this to be one transfer function and this to be another transfer function, tf1 and tf2. Now when you add two transfer functions, when the overall transfer function is the sum of two transfer functions, then what does it mean? It means that there are parallel paths. If you consider in terms of the block diagram, you will have one transfer function here, input to a summer, and another transfer function tf2 input to the same summer. So the resultant output is going to be your output, and this is going to be the input. Both the blocks are coming from the same input. What if you consider in terms of signal flow graph? This is going to be two parallel paths. Here you can take the input, gain 1 you can take, this also gain 1 output. Here you have transfer function 1 and transfer function 2. So now we will take this example, k1 by s plus a1. Let us say whatever the transfer function, we were able to get this form using the partial fraction method. Okay. Now we anyways know what is the state diagram for this kind of functions, right? Now both of them, if you keep them in parallel, you will get the actual state diagram, the required state diagram. Once we get the state diagram, then we can get the state model, right? So for the k1 by s plus a1, you have one integrator and there is going to be the loop here minus a1 gain, and here you have k1 gain, okay, and the other parts you can take 1 and 1, so that you can write the input here and output here. Similarly, the other path, this will be gain 1, integrator s to the power minus 1, what will be the gain here? Minus a2, and here the gain is going to be k2, and finally 1 here. So this will be the state diagram. Now how will you get the state model? When you assign the state variables. So we will assign the state variables. Now you can consider each of the integrator, the output of each of the integrator you can take as one state variable. So here you have x1, so here you will have what? x1 dot. Here you have x2 and here you have x2 dot. Let us now write the equations. x1 dot, if you see here, there are two paths, one is this one and another is this one, right? So x1 dot will be equal to input if you take as u and output if you take as y, then x1 dot you are going to get minus a1 x1 plus u. This is the first equation. Now what about x2 dot? Similarly, x2 dot is going to be minus a2 x2 plus u. This is the second equation. Now finally, the output equation is going to be y is equal to, there are two paths here coming from x1 and x2. So y you can get as k1 x1 plus k2 x2. This is the third equation. Now from these two equations, the first two equations, you can get the state equations. What will that be? x1 dot x2 dot is equal to x1 x2 will come here plus B matrix into U. Okay, so now x1 dot you can see that it is related to x1, coefficient is minus a1, it is not related to x2, so you will write 0. And x2 dot is not related to x1, so you will write 0 and it is equal to minus a2 x2. Okay, then what about the B matrix? You will have 1 and 1 here, because here you have x1 dot is equal to minus a1 x1 plus u. Similarly, x2 dot is minus a2 x2 plus u. Okay, so you have the matrices A and B here. One thing that you can see here is the matrix A is a diagonal matrix. That means when you use the parallel decomposition method, you are going to get the canonical diagonal canonical form. Okay, so this is the important point here. You can see one more important point here. In the diagonal canonical form, each of the x1 dot, the state variable, is dependent on its own state variable x1. It is not dependent on x2, right? And similarly x2 dot is dependent only on x2, right? So that means that we are going to get decoupled equations. You can write down decoupled equations are obtained. What is meant by decoupled? x1 dot depends only on x1 and similarly x2 dot depends only on x2. And finally you can write down the output equation in the matrix form, right? So y is equal to, this is going to be C x1 x2 plus 0 into u, because y is not dependent on u. So this is going to be k1 x1 plus k2 x2. So this is the C matrix here and this is the D matrix. Now when will you get the Jordan canonical form? When will you get a Jordan canonical form? When the eigenvalues are at least some of them are equal. Okay. In terms of the transfer function, if you see, they are going to have multiple order roots. So that means let us say f of s by some s plus a1 whole square into s plus a2. Then what will you get? If you split this by partial fraction method, then you will get a term s plus a1 whole square plus another term will be s plus a1 and another term will be s plus a2. Now this term here s plus a1 square, right? Whenever this is present, then you can be sure that you will not get in the diagonal canonical form, rather you will get in the Jordan canonical form. Okay. Now how will you draw the state diagram for this kind of function? So let us take k1 here, k1 by s plus a1 whole square. Then you can write in the cascaded form, product of two terms, right? So k1 s plus a1 into 1 by s plus a1. Okay. So now you can draw easily what will be the state diagram for k1 by s plus a1. You are going to have one integrator, that is common, and the loop gain is going to be minus a1 here, and here the gain is going to be k1. Okay. And next 1 by s plus a1, how you can draw? The integrator you will draw here, this will be minus a1 and this is going to be 1. Okay. So you will have the input and the output here. So this is the first term, let us say. We will mark these as transfer function 1, transfer function 2 and transfer function 3, right? And the numerator we can take k2, k3, right? So now this we have drawn for transfer function 1. Next we will see for transfer function 2. We will draw one below the other so that these are all parallel, right? So if you draw them one below the other, then they are going to be in the parallel form. So k2 by s plus a1, you can draw the integrator here, s to the power minus 1, and this will be k2. And what will be the loop gain? It is going to be minus a1. Here the gain is 1, here also gain is 1, right? And here also the gain 1 you can take. Now what about transfer function 3, tf3? So it's going to be similar to transfer function 2. You will have the integrator s to the power minus 1. The gain is going to be minus a2. Here gain is going to be k3 and here you have gains 1 and 1. All of these now you can draw as parallel blocks, right? So this is how you are going to get the state diagram. But there is one more thing that you have to see here. You can see that this is in the transfer function you have a third order denominator, right? S plus a1 whole square into s plus a2. So this is third order. But in the state diagram you are getting 4 integrators, 1, 2, 3 and 4, right? If there is third order, it means there are only 3 integrators. So we have extra unnecessarily drawn one additional integrator. So we can see that in these two paths, this path here is essentially the same. So if you can eliminate this integrator, then you're going to be left out only with the 3 integrators. So this now you can join here. Gain you can take as 1. So now this is the input and this is going to be the output. You can remove this transfer function 1, 2 and 3 here. Okay. So this is the state diagram. You can find out the transfer function for this state diagram and you can verify as well.